everybody. Hello, very lovely to see you all. Welcome to you all, whether you're in the lecture theatre or joining us online this evening for what I think will be a really, really fascinating session. In perhaps yet another year when here on Earth life seems sometimes bewildering and exhausting, we thought that perhaps we would step back, take the long view, and look at the really, truly big picture. Leave planet Earth and head into space. And this year we have a series of talks term by term on that theme. Today, we have a chance to hear about the latest research and the newest thinking, which is helping understand the universe, its origins, its dimensions, and our place in it as our species makes further inroads into space. Uh, in a moment, we're going to be joined by three wonderful researchers. Professor Michael Hobson, Fellow of Trinity Hall and University Professor of Astrophysics. His research interests include cosmology, in particular the primordial fluctuations in the cosmic microwave background radiation. He'll tell us more. And he developed some of the Bayesian statistical methods that enabled the first detection of these fluctuations. He's also involved in using some of these statistical techniques and data science back here on Earth, meeting challenges here. We're also joined by Thom Colledge, who's a Royal Air Force officer, currently with Trinity Hall reading Politics and International Studies. Before joining us, he was commanding the UK's low Earth orbit space surveillance facility in North Yorkshire. He's researching low Earth orbit space sustainability and next will be assigned to the MOD responsible for UK space security policy. Dr Amy Bonsor has kindly joined us from along the river at Queen's College. She's an astrophysicist, the Royal Society University Research Fellow, and Associate Professor at the Institute of Astronomy here in Cambridge. She studies planets orbiting our sun and also other stars, looking at how they form and what they're made of. Her work also aims to further our understanding of our own solar system, our planet, and even perhaps the origins of life. So this event is being live streamed and recorded for the duration, and the recording will be available to view afterwards. At the end of the presentations and our panel discussion, there'll be a chance to ask questions, so think about that as we go along. We'll have a roving mic. And for those of you joining online, you can submit any questions for the panel via the live chat function. I'll explain all of this again when we come to it. But first, we're going to hear a series of short presentations from each of our guests. And first of all, I'm going to invite Mike Hobson to the lectern.
Thank you, Master. So when I'm asked what I do for a living, and I reply that I'm a cosmologist, thank you, the reaction typically falls into kind of two very distinct categories. In the first group, there's a kind of vague and panic-stricken look that comes across people's faces as they're desperate to get somewhere else. But in the second group, which is thankfully the larger, one encounters a genuine interest. And people very often admit to having rather long-standing and deeply held questions about the origins of the universe, and inevitably, therefore, of themselves. And in fact, it's one of the greatest benefits of studying cosmology that it's an academic discipline of such interest to so many and of relevance to all. Now, in trying to explain cosmology, one of the greatest difficulties is communicating the magnitude and the range of the physical scales associated with the structure present in the universe and the size of the universe itself. Now, in seminars, we have audiovisual aids, such as, and I have one here that I will be showing you a few slides from as I progress. But often the imagination is a much better tool than a laptop. And so I want you to imagine for me the following scenario. And in fact, it comes from a movie that some of you may know. Imagine a movie that starts with a couple picnicking in Central Park, New York. And as the movie progresses, it zooms out by a factor of 10 every 10 seconds. This is a movie you can probably find on the internet nowadays quite easily. So gradually, the picture, the screen encompasses the whole of Central Park, then New York itself, the eastern seaboard of the United States, the whole Earth, the Earth-Moon system, and so on. And as the field of view continues to grow, it eventually includes our entire solar system, consisting of the Sun and all of its planets. I still think there are 9. Then nearby stars will come into view, followed by more distant stars. And gradually one gains a perspective of seeing our Sun located on the outer limb of one of the spiral arms that make up the majestic swirl of our own Milky Way galaxy, which contains over 100 billion stars in total. And you may be used to looking out at night and seeing the Milky Way band in the sky. That's a Milky emission, that's the plane of our galaxy. But in fact, if one were to be able to step outside of our galaxy, then you would find that it's quite sobering to realize that we live in the unfashionable galactic suburbs, far away from the bright lights, quite literally, of the bustling galactic centre, although this should be a familiar concept to anyone who lives in Cambridge. But this is not the end of the movie. Remember, it increases in size by a factor of 10 every 10 seconds. And we see our Milky Way grow progressively smaller, surrounded by nothing but the empty void of space. Our galaxy is an island universe, an oasis of light and life in the dark cosmic desert. But is not unique, and soon one sees another galaxy come into view, called Andromeda, followed quickly by a myriad of other galaxies, each different in the details of its size and shape, but all as vast as our own Milky Way and separated from one another by distances of over 100 times the size of any individual galaxy. And I could illustrate that for you with a very old piece of technology called the Hubble Space Telescope. And this is a very deep stare into the universe. You might recognize that constellation. I hope so. And progressively, you're going to zoom in and zoom in and zoom in. Each of these is a different survey that was taken. Eventually, we'll get, after a few surveys, to a little patch of sky observed by the Hubble telescope. And what you see there is, those aren't stars. If you look, these, have I got a pointer? Yes, I have. These are, pointer, yes. These are little swirly galaxies like our own. So you look out deep into the universe and there are hundreds of billions of galaxies just like our own. And to give you an indication of how much structure there is in the universe, that patch of sky roughly is the same size as if you were to hold a 10-pence piece at arm's length, and it's the size of the Queen's eye. Okay? That's how much structure there is in the universe. Billions of galaxies. So gradually the movie continues, and our perspective shows that 1,000 or so galaxies nearest to our own form a roughly spherical ball of galaxies called the Virgo cluster. But this cluster is not unique. Indeed, there are around 1 billion such clusters in the observable universe. And on the largest scales, these clusters of galaxies themselves are distributed into superclusters, which are arranged across large sheets that surround vast empty voids in a manner not too dissimilar to the distribution of material in a bathroom sponge. Let me show you what it looks like. That's just a slightly clearer picture of the Hubble Deep Field. But if you look out, again, very old survey, we've known this for some time. You look out into the universe along 2 fans coming out of our galaxy. What do you see? Each dot there is a galaxy. This is a very old, very small catalogue with only a couple of 100,000. Now we've mapped tens of millions of galaxies, okay? But you see that, each dot is a galaxy, and you have this vast structure which has a certain statistical characteristic about it, okay? And there exist, on the larger scales, these, as I said, these clusters and superclusters are arranged across large sheets and voids, as you can see there, like a sponge. Now, to arrive at the largest scales of our observable universe, if I were to play this movie, would take about 4.5 minutes. So that's 270 seconds. So on the largest scales of our universe as a whole, just to give you an idea of the size of things, our universe is a scale about, because it takes 270 seconds in the movie, it's a scale of 10 to the 27, that's a billion, billion, billion times larger than the scale of our everyday experience, such as a picnic in Central Park. Now, this is all expressed rather lightheartedly, but in a physically accurate manner, in an extract from none other than The Hitchhiker's Guide to the Galaxy, which says the following. The simple truth, it notes, is that interstellar distances will not fit in to the human imagination. Even light, which travels so fast that it takes most races thousands of years to realize that it travels at all, takes time to journey between the stars. It takes 8 minutes to journey from the sun to us on Earth, but 4 years to journey from the sun's nearest neighbouring star, Alpha Proxima. For light to reach from one side of the galaxy to the other takes around 100,000 years. Now, if Douglas Adams had wished to entertain and inform his readers further, he might also have mentioned that light requires around 2 million years to travel from the Milky Way to our nearest neighbouring galaxy, Andromeda, and around 15 billion years, as you see here, to cross the observable universe. Now, compare that with the light travel time from here to the moon, which is 1 second. That's trying to get across the idea of the size of cosmological scales. But then you're faced with a really tricky question. What's the origin of all this structure? What could it be? And this is one of the cornerstones of modern cosmology, this question. And the answer to it, really, we can only hope to answer it because nature has been extremely kind in providing us. I will just skip through these because I will show you this. Nature's been very kind in providing us with a massive clue, okay? The primordial fluctuations in the cosmic microwave background radiation, master, come about here. Recombination, about 300,000 years after the Big Bang. And so that's when the universe was about kind of a thousandth of its current age. So what happens is, at this point in the universe's evolution, we get effectively a childhood snapshot of the universe, what the universe looked like when it was a little baby. And that's the subject of my own research to a large extent. And the cosmic microwave background is the oldest light in the universe and has been traveling through space essentially unhindered since the universe, as I said, was about a thousandth of its current age. And so if one can map that, what you see is tiny fluctuations in that radiation, and those fluctuations collapse under gravity to form all of the structure we see. And to understand why that happens, we need to turn to Albert Einstein. Now, Einstein's theory of general relativity is a masterpiece, but it allows for something very surprising. In Einstein's theory, gravity can push as well as pull through something called the cosmological constant. In other words, objects can repel. And in fact, they repel more strongly the further apart they are. Whereas the attractive force obviously attracts more strongly the closer things are. So in some circumstances, you can get this repulsive behavior of gravity. And these circumstances are precisely those that one expects to occur in the very early universe. So according to Einstein's theory, this gravitational push caused the universe to expand very, very quickly when it was just a fraction of a second old. I will skip through to here. There's kind of idea of the universe expanding very quickly through a very small period. And in fact, this is supposed to have happened when the universe was really just a fraction of its current age, 10 to the 35 seconds after the Big Bang, and it's called the period of inflation, inflationary epoch. And during that epoch, the universe expands, according to our current best theory of how the early universe works, by a factor of a billion, billion, billion times. Remember, we've heard that before. And it does it in about 1 million billion billion billionth of a second, after which the expansion continues at a more sedate rate. Now, think about what I said regarding the scale of everyday experience, a picnic, and the larger scales in the universe. That also had a billion, billion, billion. So what does that imply? It implies that the largest structures that we see today can be formed from very small scale fluctuations, in fact, fluctuations on subatomic scales, if you do the calculations correctly. And so that subatomic scale is dominated not by general relativity, but by quantum theory. And so in order to understand the structure formation in the universe, you have to marry general relativity and quantum mechanics. Quantum mechanics, of course, is one of its basic predictions is that quantum fluctuations occur on small scales and particles continuously pop in and out of existence. And if you calculate how that happens and how those fluctuations evolve as the universe expands, you can predict the statistical properties of the fluctuation and compare it with the cosmic structure that I've just shown you all. And amazingly, when you do that comparison, they match together beautifully. It's therefore led to what, in my opinion, is a most profound and surprising discovery made only in the last kind of 20 years or so, really. As one looks out into our universe and observes the vast voids, sheets, superclusters, and so on, what you're really looking at is the physical imprint, vastly expanded through inflation, of tiny quantum fluctuations that occurred on subatomic scales in the earliest stages of our universe's life. Hence, all that we see, including ourselves, owes its existence to the inherent uncertainty and chaos that characterizes the quantum world. Let's take a moment to think about that. But on reflection, at the start of a busy examination term, perhaps that's not too surprising after all. So I can just illustrate this for you with one final plot. So we have quantum fluctuations on the smallest known scales become the seeds of cosmic structure formation. Essentially, inflation makes quantum fluctuations turn classical. And here's a dreadful movie of quantum fluctuations. That's my best PowerPoint interpretation of quantum fluctuations, which evolve through their own self-gravity. They are then, they lay down the seeds of structure. That leads via inflation to classical perturbations imprinted in this early childhood snapshot of the universe when it was just 1,000th of its current age, which we can observe. And those fluctuations, when they collapse gravitationally, lead to all of the cosmic structure I just showed you. So the largest scales are just the smallest scales, but expanded through inflation. Quantum theory and general relativity, for once, working together in a meaningful fashion. So I'd like to stop there and hand over to, I think it's Amy next. Okay. And I'm told if I... Thank you.
Thank you. Okay, so I'm also an astronomer. And so I'm going to talk about things on a very, very different scale. And so I thought I'd start out by kind of showing a picture. There we go. Of one of the telescopes that I like to use quite a lot. I've also got a lot of observations from the Hubble telescope, but of very different things to what Mike had here. But this is the VLT, which is the very classically named Very Large Telescope. And you're just seeing a laser guide star there, but what you can see is a mass of stars across the Milky Way here. And when we look at all of those stars, what we want to learn as astronomers is, what are they like? Are they the same as our sun, or are they really, really different? And I'm particularly interested in the question of whether these stars also have solar systems around them. And even, do they have planets like our own planet Earth, or like Jupiter and the other planets in the solar system? And we're super lucky because we're really in a kind of revolution of discovery. In the last 20 years, we've gone from discovering the first planet around a star, similar to one of the ones you can see here, to being in a position where we now know over 6,000 stars that have planets orbiting around them. And those planets are all very different. So this is just an artist's impression of what some of those planets might be like. We're actually very limited in the information that we have about them, apart from knowing that they're there and what kind of size they are. But this kind of, I love this image because it gives you some kind of idea of the diversity of the planets that we found. So I was actually at school when I first learned about exoplanets, and I went to a lecture, probably rather like this, when I was trying to decide about university. And the professor put up at the time what were the first 6 exoplanets that had been found. And those planets were nothing like anything we have in our solar system. They were several times the mass of Jupiter, and they were going around their star every couple of hours. And that was why we could find them, because every couple of hours is something that you can observe on human timescales readily, and they were very, very big. And they were big balls of giant kind of gas, just like Jupiter and Saturn. But illustrated here, you can kind of also see that we're now moving down into what we call the kind of Neptune regime, where things are smaller than Jupiter, and even into sub-Neptunes, still these kind of gas giants, but now much, much smaller. And then in the last 10 years, we've even been able to move down into kind of rocky planet regime. So we're starting to find things that we call super-Earths. So those are rocky planets, but that could be maybe 10 times as massive as our own planet Earth. And then we're also discovering planets that are about the same size as Earth, and about the same mass as Earth. And so we're really getting down towards those planets that really could truly be analogues of our own planet. But what we've yet to find is an Earth-like planet that orbits a star that's like our sun. So the planets that we find, they're much, much closer in, and they orbit much, much faster. And that's just because it's much, much easier for us to find them. We don't have to wait for several years for the planet to keep going round for us to see it. But I think it's good to kind of think about that quest for finding a planet like our own Earth. And I put up this image of our planet because I think it's useful to kind of start to think, well, what are we going to learn about that planet when we find it? So this is an image that's taken from a near-Earth satellite, right, kind of tens of kilometers above the surface of Earth. And yet, if you were to just look at this image, how many of you could guess whether or not there was life on this planet, let alone complex animal life that we all know? Like, we can see that there are clouds. We might be able to see that there was oceans through looking at that, but really we're very limited in the kind of detail that we can take. And that's from tens of kilometers away. When we're looking for exoplanets around other stars, we're now looking at things which are tens of light years away. And so just we're very, very limited in the kind of information that we can find out about these planets. And so we have to use as much as we can to kind of try and work out what these planets might be like and what their surfaces might be like. And one of the big questions, which is super fundamental, is what are those planets made from? And so if we want to know start to think about the surface conditions or the kind of geological processes on a rocky planet, we really need to know much more about what the planet's made from, not just whether it's a rock or a ball of gas. We need to know in detail what the composition of those planets are. And that's actually a very hard question. And one of the reasons it's a hard question is because when we find those planets, we're not taking pictures of them like the picture I just showed you of Earth. We're actually indirectly finding them by other means. And one of the ways that we do that is something called the radial velocity technique. So this is just where we look at the star and we don't see the planet at all. We observe the star in very great detail. And what we see is that the star is doing a tiny, tiny little circle. And the reason the star is doing that tiny little circle is because the star is going around the planet at the same time as the planet is going around the star. And so the star is bright, and we're able to observe stars very, very well. And so we can use that to detect that planet. And that tells us what the planet weighs. It gives us its mass. We're kind of using our scales to weigh what that planet is. And if we're really lucky, that same planet might be between us and the star. So when we look at the star, that planet's going round, and it might occasionally sit in front of the star and block some of the light from the star. So if we measure how bright that star is over time, we might see that there are regular dips in the brightness of the star, and that's called a planetary transit. And transits are really powerful because they tell us how large the planet is, because we know how much light has been blocked compared to the size of the star. And so we can work out how big that planet is. And so from those two things together, it doesn't take much to kind of guess that we can know what the density of a planet is. We have a mass and a radii, but we can only do this for a very small set of the planets that we know. And from an even smaller set, the really exciting next frontier is to not only look at the planets, but actually to look at the light that's going through the atmospheres of those planets. And in doing that, you're able to see some of that light is absorbed by things which are in the atmosphere of those planets. And so we're able to characterize what those atmospheres might be made of. And so here I've put up a kind of famous example of WASP-18b. It's a big gas giant where we're able to see water in the atmosphere of that planet. And that's because it's a really bright planet, and it's more close by, and we're able to kind of characterize those atmospheres. So in my group, we kind of wanted to think about a different way of learning about all of these things. And we kind of asked that question, well, if I was a lab scientist and I wanted to study what a planet was made from, well, I would take that rock and I would take it into the lab, and I would look at it under a microscope, and I might use that to kind of try and interrogate what that rock was made from. We do that with meteorites, rocks from space that land on Earth. We're able to use mass spectrometers to work exactly what kind of composition they have, and that's been so powerful in understanding the history of our solar system. But the thing with astronomy is that we're talking on big scales, and we can't go out there and collect things. We learnt about how many light years it takes to bring something back from the nearby star. It's just impossible. But instead, what is amazing about astronomy is that we can look for our own laboratory, because we have so many manifestations of things happening. The universe is massive, and we can, if we want to study how our solar system grew up, we look at another star that has a planetary system but is younger, and we use that to study it. And so here we found our kind of own laboratory where actually in space, naturally, these planets are being smashed up, and there's a kind of microscope or equivalent that we can use to look at them to see what those planets are made from. And that laboratory is actually a star that's called a white dwarf. And so that's the faint remnant of a star like our sun. It's what's going to happen in 5 billion years' time. When our sun runs out of fuel, it will lose its outer layers and leave behind this tiny faint remnant that has a very, very high gravity. So I've kind of put here next to the Earth, and that's because white dwarfs are about the same size as the Earth, but they still contain about a mass of the sun. So the gravity is super high. And what's really nice about that is it means that anything sinks very rapidly into that white dwarf. So we're able to look at the surface of that white dwarf. There should be nothing there but hydrogen and helium, because anything heavier has sunk well out of sight. But instead, in a handful of these kind of special laboratories that we found that some of these white dwarfs have a sprinkling of kind of planetary dust on the outside of them, and we're able to use these to study what planets are made from. So this is an artist's impression of a kind of chunk of a planet here that's being turned into dust, and it's kind of sprinkled onto the outside of this white dwarf. And these are the things that we're really interested in my group in using to study what planets are made from. And in order to do this, we use something called spectroscopy. So we're splitting the light up into all the different colors or the different wavelengths that you can get in the light. And so this is a spectrum of a white dwarf. You can see how bright it is as a function of the wavelengths. And on there, you can see that there's a lot of these kind of very narrow features here, which is where light has been absorbed by things in the atmosphere of that white dwarf. And there's a nice little color code to kind of help at the top. So you can see there are a whole load of iron lines and calcium lines, magnesium lines. And this is all planetary dust that we're seeing in the atmosphere of that white dwarf. And these white dwarfs absolutely incredible, because what we can do is we can work out exactly the composition of that planetary material. We can say how much calcium did it have, how much iron did it have, how much magnesium did it have, how much nickel did it have. And so even better than kind of studying the atmosphere, we're able to study the mineralogy of the rocks that might have formed these kind of planets. And so in our group, we're trying to use this to understand how planet formation determines what rocky planets are made from. And we're even able to see some geological processes, so things like um, our Earth formed an iron core and has a rocky mantle, and we're able to see evidence from these compositions that we're seeing that some of those geological processes have happened in exoplanets, which are kind of hundreds of light years away. And so I'm very excited about the field in general, and I thought I kind of would finish up by putting up one of the next big things that's going to be happening looking for exoplanets. So I said we are yet to find that kind of rocky planet where we really want to know what it's made from, what the surface conditions are like around a sun-like star. But this is an artist's impression of Plato, which is a space mission that's going to fly towards the end of 2026. And Plato is going to find for us hundreds, if not thousands, of new exoplanets, but it has the aim of finding a rocky Earth-sized planet around a star like our sun. And so I think I would watch this space, because the next 5 years of exoplanet research is going to be very, very exciting. So thank you for listening.
Hi, everybody. As Mary pointed out at the start of the presentation, I'm here at Cambridge for 9 months on a sabbatical reading politics and international studies. But my day job, actually, before I got here, was that I used to command the UK's low Earth orbit surveillance sites. So up in North Yorkshire, if you're a heavy radar geek, then this is a solid state phased array 10 megawatt radar. And if you're not into radars, then all you need to really understand is that it throws energy up into space, about sort of 3 nautical miles or 3,000 nautical miles or 5,000 kilometers into low Earth orbit. And it effectively enables us to track anything that's moving in that space down to kind of the size of a can of Coke. And originally, it was kind of developed during the Cold War as a way of kind of tracking complex ballistic missiles against us and our allies. But actually, it's turned out to be extremely useful in looking at kind of the development in low Earth orbit in the round. And we spent almost all of our time looking at satellites and wondering sort of why they were where they were they where we expected to be, and were they behaving in the way that we thought they were. And it was a really, really eye-opening job, especially in the period that I was there. And I kind of came away with a couple of observations, really. The first is that, space now is extremely critical. It's also extremely contested, it's congested, and it's very competitive. But it's also got a bit of a PR problem, because largely it's kind of out of sight, out of mind. And as part of my job, we'd routinely bring parliamentarians and secretaries of state for defence and things up to Fylingdales. And often we had to put them in the bit of the building that was the least classified, because a lot of them don't have any security clearances, and try and explain to them why space is so important in the 21st century and how it's fundamentally critical national infrastructure now. So I'm going to start talking about the criticality of space, and I'll sort of go through the further 3 or 4 points over the next 10 minutes or so. And I'm going to look at it through the lens of security and sustainability, because I see both of these things as two different sides of the same coin. So if you think about criticality of space, it's very difficult to imagine how we would operate as modern human beings in the 21st century without it. I mean, the most obvious thing is the fact that everybody relies on GPS to figure out where they're going and how they get there. But actually, that time signal that comes from that same satellite is absolutely fundamental to all of the cryptography that you use every day. Every time you log onto your bank, you send a sort of code, and that time standard is absolutely fundamental. Communications are largely now delivered by space infrastructure and architecture, and it's super important. And we saw the importance of Starlink, for example, in the Ukraine. But actually, we would never think about sending a carrier group across the world without the ability to communicate using satellite communications. And then, of course, you think, well, it's almost unconceivable how we'd operate without it. But there was a report in 2018 called the Blackett Report that tried to quantify what would happen if we had a day without space, and it's difficult to conceive. But actually, it's kind of they reckon it would cost the UK economy alone £5 billion a day if we didn't have space. You think, well, that's not going to happen, is it? But actually, there's something called the Carrington effect, which happened all the way back in 1859, which is a very large solar storm, a coronal mass ejection, that even back in the day caused humongous power outages and fires in all of the sort of local telegraph stations, because the effects of space weather, it can be massively significant. So it's definitely something worth thinking about. So if you think about the importance of all this stuff that's sort of circumnavigating the globe at once every 90 minutes at 10 kilometers a second, you start to think, well, actually, this is clearly what Clausewitz would consider to be a center of gravity. It's something that if you can attack and deny an enemy the use of, then it's something that's going to be used to defeat them. So this goes on to my next point about space being contested. And when I was a kid, there were really only 3 operational domains. There was the air, the sea, and the land. But I think everybody recognizes now that when we talk about 5 operational domains, we talk about space and we talk about cyber. And if you think about the kinds of threats that might exist, I think if we were to bring in a whiteboard now and ask you all with a glass of wine to sit down and sketch out all the ways that you could interfere with somebody's stuff in space, it wouldn't take you long to come up with a fairly comprehensive list. And if you can think of it, you can be fairly certain that somebody else has probably thought about it and might be trying to think about it. So the sort of some very basic examples really sit on a scale of sort of very temporary effects that are extremely deniable, all the way through to things that are very undeniable and extremely permanent, and would probably be considered a significant act of war these days. And it's really interesting to sort of think about this because it's very difficult to understand what is happening in space. It's very transparent, it's easy to look through, but actually it's very big, everything's far away, there's lots of it, and often a lot of the stuff that's happening is in bits of the sort of electromagnetic spectrum that you can't necessarily see by eye. So it's a thorny problem to resolve, right? And when you sort of want to try and understand what's happening in space, international partnerships are massively important. So this is just the US space surveillance network, just one example, but many countries and coalitions have their own version. But you can already see that there has to be sensors all over the globe in order for this to work, because you can only see certain sections of the sky from certain areas. And if you were to flip it over, you'd see an awful lot of stuff in partnership with the Australians, and a massive space fence radar in the South Pacific, for example. And the Russians have a similar system, and the Chinese have a similar partnership. So as you can see, despite the US kind of in the geopolitical sphere beginning to appear a little bit more isolationist, you can't operate in the space domain without partners. Everybody saw that JD Vance went to Greenland recently. Very hot news topic. What a lot of people don't understand is that he visited a space base, which is exactly the same radar as I used to operate in Findingdales. And that's the kind of geopolitical significance of why people like the Americans, for example, are really keen that they don't lose access to certain parts of the world. In terms of behavior in space, is also really interesting. And part of my research is kind of about, how you drive the correct kind of behavior. But actually, there aren't a lot of legally binding treaties in space. The classic one is the Outer Space Treaty. It was published in 1967. And it only really says 4 things. Don't put a nuclear weapon in space. Don't colonize anything in space. Anything you bring back from space belongs to every single human being on Earth. And if you get stuck in space, we'll all try and help each other in the same way that you would if you were a stranded sailor on the high seas. And everything else is extremely open to interpretation. There are a couple of other treaties that were written. There's one about liability, and there's one about registering items also in the sort of like late 60s, early 70s. But there hasn't been a legally binding treaty in space since 1967, which is the Moon Treaty. And that's really just a restatement of the Outer Space Treaty. So everything really seems to operate on sort of soft law and non-binding and sort of instruments about normative behavior, which is something that I'm very interested in. To give you an example, direct-to-send anti-satellite weapons are, extremely disruptive. A lot of countries have tested them: the US, China, Russia, India. In 2007, the Chinese shot down a satellite of their own that was effectively dysfunctional, and in that one event, increased the amount of debris in low Earth orbit by 30%. And in 2021, the Russians did another similarly disruptive test, which transpired to be a kind of pre-Ukraine flex, just to demonstrate they had the capability and the intent, which is equally important, but actually created a debris cloud where no one really knew where it was going, to the point where all of the astronauts and the cosmonauts on the ISS got into their pressurized capsules just to make sure they didn't get struck by something that was whipping through the atmosphere or through space at 10 kilometers a second, which would have caused considerable damage. So this brings me on to the next thing that I want to cover, which is kind of how congested space is coming, or certain parts of space. I mean, space is very big, as we've already discussed today, but in certain bits, particularly in low Earth orbit, there is a remarkable amount of activity, and that is only increasing. The number of actors that are now involved is rising exponentially. To the point now where, actually in the 70s, a scientist called Kessler sort of postulated that there's a very good chance that if a piece of debris was to strike another piece of debris and start a chain reaction, it could get to the point in which, like nuclear fission, for example, we lose control of that chain reaction and the entire low Earth orbit is denied, which is something that is really worth considering. So it's very important that we kind of take this seriously. This is a diagram of what Elon Musk is proposing with Starlink, and that's just one constellation. And there are lots of companies and countries that are really interested in putting big constellations into low Earth orbit because there are lots of advantages about doing so. It's very difficult to jam, it's highly proliferated. If you lose one satellite, it doesn't really matter. So this feels like it's the trend. And if you look at this kind of figures, you can see, hopefully that's legible, but the extremely large exponential growth at the sort of right-hand side is as a result of constellations that are starting to be put into space. And this kind of brings me to the last C, which is about competitiveness, right? Because the cost of putting stuff into space is dropping significantly. Right? When I was a kid, if you wanted to put a kg of payload in space, you put it on Atlantis and it cost you $50,000. Nowadays, we could all put 20 quid into a pot and pay Elon Musk £2,000 to put a kg of payload into space. And in 10 years' time, I suspect it will be 50 or 60 bucks to put a kg of payload into space, which is really interesting because actually there's lots of questions about who is the arbiter of good taste when it comes to putting stuff into space. And a lot of my research is about my inclination that actually some of the private actors who are operating space are being significantly more innovative when it comes to sustainable behavior than some of the nation states. So I've seen some really good behavior by some of the commercial actors and some bad behavior, but it's about sort of drawing out the reasons why that is. And in a sort of free market economy, you've effectively got, as people are becoming more environmentally aware, there's a driving realization in order to sort of make money, you have to have a sustainable angle, but it's also really important to protect that environment as a global commons, right? So what of the future, right? There's a few things. I think that, we saw really interestingly at the end of the Cold War, a lot of nation states start to really sort of, profit from the peace dividend and start to reduce their space budgets. And there's been some hard lessons about that. Okay, for a while, the US had no ability to put stuff into space on their own, and they were relying on either the Russians or commercial actors. the Ukraine was really, really interesting because effectively that was the first time a commercial actor had enabled a nation state to effectively continue to be combat effective as a result of the fact that they provided a communication system that was extremely unjammable, and therefore enabled the Ukrainians to continue. But actually, we also saw a lot of political pressure from some of Starlink's other customers in other parts of the world to think very carefully about who they were siding with. And it was very clear that some of the individual nations were starting to lose a bit of agency about that. So hence we've seen a lot of interest in national space programs again. I think it's really interesting to think about debris. That's going to be something that's fundamentally critical. It's kind of recognized as one of these global tipping points that if it goes wrong, it's going to go badly wrong. So, and there's a lot of money to be made in something called active debris removal. So effectively, companies who are now putting stuff into low Earth orbit in particular with the ability to grab hold of stuff and sweep it up, or use nets to collect things, or put a big sort of sail on it so that it effectively causes it to deorbit more quickly. But that is dual use technology, right? If you think back to the slide about all the different threats, one person's rubbish is another person's stuff. And therefore, if you start interfering with their things, that very quickly causes an issue, especially when we sort of talk about liability in space, because the only rules around liability are that any nation that puts something into space is responsible for it. But that was kind of agreed in the 70s. But what happens now if you're a private actor launching, registered in the US, launching from a site in New Zealand with a payload from a third country, and then you hit a fourth country? It's super complicated and hasn't ever been tested properly in the court of law. So that's very interesting. Hypersonic technology is becoming very prevalent. As I said up front, right, you are not allowed to put a nuclear weapon into space. But then what space, right? Is space a complete orbit? If you only put it fractionally in orbit, does that count? So you have fractional orbit technology now that could deliver a nuclear payload anywhere in the world in 90 minutes. And it doesn't technically contravene a convention. Similarly, how do people like myself who are sitting there monitoring low Earth orbit, trying to understand where the threats are, pick out genuine threats from all of us who are going to Barbados using hypersonic technology, which means that we can fly there in 90 minutes? So that picture is going to become very complicated and congested. I think that there's going to be a lot more kind of in-space manufacturing and refueling and stuff, because actually 90% of the problem of getting out of the Earth's atmosphere is getting out of the Earth's atmosphere. So if you can do more stuff when you're already out of there, then you can give yourself significantly further range. And that is why things like lunar and cislunar exploration are super, super topical at the moment. Because if you can set yourself up on the moon, and although you're not allowed to colonize it, but first come first serve, right? If you're there and you're operating, nobody else is going to be there and operating on that particular piece of real estate. That then enables you to use that as a leap pad to other parts of the sort of bigger space picture. But potentially you could use some of the ice water as fuel. So there's lots of things that are kind of people are thinking about. And actually, some of the traditional sort of leaders in the field, like the Americans, are a little bit nervous about the capabilities of some of the emerging nations, like the Chinese, who I think are on track to have the first space, proper space base, if it plays out as it has been so far. So I'll probably leave it there, and then I guess in questions we can see what people want to sort of dig into in a little bit more detail.
Great. So I'm going to welcome our panel up to the stage. So thank you all very, very much. And you have taken us far, far away, far back in time, far into the future, maybe not so far into the future. Really, really interesting. We're going to just talk together for a few minutes, but then we will open it up to questions. So, anything that interests you, the panel will be ready to give it a go. Mike, I thought I'd come back to you, sort of where we started. So you took us back a really, really long
That's part
way and time to what you call the childhood of the universe, and these absolutely minuscule quantum flutters and fluctuations. In your work and with your colleagues, are you now trying to think about how to get back even further? And
Right.
is there any data or mechanism or analysis or way of doing that?
Right. Well, the singularity, the Big Bang, is just a fig leaf for our ignorance. Because I mean, if the thing I didn't really have a chance to go into is all of the structure that I sort of introduced you to, um, you can pretty quickly figure out that it's all moving away from each other. Okay, essentially by a Doppler effect, the same effect as you would recognize from an ambulance coming past you and rising and then dropping tone of its siren. So you can look at uh, spectral lines, which Amy was describing in her talk, and you can see that they're shifted in frequency and the universe is expanding. Okay, so all of that structure is moving away from one another. And like any gas, as the universe expands, it cools. And so what I showed on one of my timelines is that the universe actually goes through a series of phase transitions as it cools. The way cosmologists think is you just wind that clock backwards. Okay, so if you start now and you go backwards, then the universe gets denser and denser and denser and hotter and hotter and hotter and hotter. And the further back you go, the more extreme the conditions become, and the the better the theories of physics one needs in order to be confident that one can describe what's going on. Okay, so we can get back pretty far. We can get back to tiny fractions of a second, kind of 10 to the minus 10 seconds. If you have if you project back to this 0 point, you can keep going, and it gets very dense and very hot, dense, high energy. So you're working with more extreme physical theories. But there comes a point when your physical theories have to become speculative because it's impossible to perform experiments that can emulate those, or simulate rather, those physical conditions. And so the theory of inflation, which I described there, has some realistic physical components to it. The whole theory is based upon the existence of a particular type of particle called a scalar particle that was postulated. Fortunately, we now have an example of one, perhaps not the inflaton, the Higgs particle is a fundamental scalar field, and it was a bit of a relief to cosmologists as well as particle physicists when that was found, because it meant that we weren't entirely crazy in postulating the existence of this scalar field in the early universe. And so if you try and think how that works with gravity, you get all of the behavior I saw. But if you try and go back further, you enter a regime where the calculations, inflation is about as far back as you can go, where general relativity and quantum mechanics play nice. Okay, broadly.
Yep.
If you try and go back further than that, the gravitational fields themselves become so strong that you can't do, basically, the calculations I work in, you do quantum calculations in a classical gravity background. Okay, so you've got general relativity describing how gravity works, you've got quantum theory describing interactions, and you can do one in the background of the other. You try and push it back further, then the space-time itself, the gravitation interaction, becomes so strong that general relativity breaks down. And so at that point, it's anyone's guess. And so, as I say, the Big Bang is a fig leaf for our ignorance of physics. And ultimately, what we're all looking for in theoretical physics is a way of being able to describe the gravitational interaction quantum mechanically. And if we ever achieve that, we will be able to push back the clock even further and perhaps understand whether, it is a singular event, or whether you have a much larger substrate and different bits of the universe drop into this inflationary state and you're in one little bubble of a much larger entity. But at the moment, inflation's about as far back as we have any confidence that we can go.
But great, because there's plenty more work to do for future cosmologists. So, we've been talking very much about the origins of the universe. Amy, you begin to take us to sort of the origins of life question, or life as we might here on Earth recognize it. And there are you and your colleagues, hunting for the rocky planet. mean, do you get frustrated with how human beings like us here on Earth are always sort of banging on about, the search for life? And are there other creatures out there? Is it interesting to you as a consequence of your work, or
Um,
just an
so
irritation?
I think there's a lot more. There's a whole range of interesting questions that kind of throws up. And I think I said before, one of the things that I'm fascinated by at the moment is actually our solar system. We are living in one tiny snapshot in time, right? And what space enables us to do is to look at other systems from earlier snapshots, right? That might one day become something like our solar system. And what's really interesting about that from the point of view of life and origins questions is that we can start to think, well, what was it that enabled our planetary system to form in the way that it is? What was it that happened that enabled us to have an Earth rocky planet at 1 AU, so 1 astronomical unit from the sun, with just around the right amount of heat that we can have liquid water on the surface? Does it matter that we have Jupiter outside protecting us from being bombarded by comets from the outer solar system? Or could we have been a different planetary system where we had Jupiter inside? How would that have affected the existence of a kind of rocky planet and potentially then its habitability? And so they are really important questions that are kind of at the forefronts of where we're pushing our knowledge. But I think it's also important to remember when we're exploring planetary systems around other stars, they are all fascinating in their own rights. And the fact that we can find planets which have 10 times the mass of Earth, but which are rocks, and we have nothing like that in our solar system. So what is this super Earth planet we call them? What are they truly like? What geological processes might happen on them? What might the surface be like? How are things different when you have that much more mass?
Yeah, and the two of you, then I'll come to Tom. But you're both working in sort of astrophysics and cosmology, but in very different fields. When you think about each other's work, does it have implications? I mean, might Amy discover something that would be, literally a sort of rock in the works of your work, or is there anything about what Mike's thinking about the expansion that might complicate how you understand the planets?
Go.
Oh, you perfect harmony.
Uh, um, I think there is a sufficient separation of scales that one can think about the sort of problems that Amy looks at relatively independently from the sort of issues that the cosmologists, such as just as I, care about. There are, as I said, the real problem for cosmologists is understanding physics at very high energies, densities, temperatures, which one would never encounter in the sort of scenarios that Amy considers. From an everyday perspective, they are extreme temperatures and densities and pressures that can exist on these planets, but not in the context of sort of fundamental physical theory as one pushes back to very early timescales in the early universe. So I think, as you would have noticed, that the interesting thing about the universe is the fact that there are these sort of scales that it's not a scale invariant entity, right? You have scales around planetary size, you have stellar size objects, and they conglomerate into solar systems, and then you have huge great gaps between the stars, okay, but they all agglomerate into galaxy size things of about 100 billion stars. And you have these galaxy-sized entities, and then vast distances between those, and they all agglomerate into clusters of galaxies with, billions of galaxies. So there's this really quite profound separation of a few scales, and that means that the work that we do can be done broadly independently of one another, I would say.
Agree with that. I think what is kind of exciting is that sometimes the technological developments for observations that we need actually benefit both communities massively. So Hubble telescope is a prime example, right? We're both using that to do cutting edge science. But even things like there's a dark energy survey at the moment, DESI, and I'm using it to look at white dwarf spectra because they are in the field, and the development of that kind of technology has been amazing. And
So technology and sending technology into deep space brings us kind of back, Tom, to some of what you were talking about. So, 50 years ago, the notion that there would be all this stuff in kind of lower or mid orbit would have been unimaginable, and yet here now you're having to think about that. We're having to think about that, and you listen, especially to what perhaps Amy's talking about with some of these probes. Are you sitting there thinking, give it time, and actually some of the same issues may arise, or maybe people are already thinking about how to make further space research in your contested, congested, competitive world
I think up
relevant?
initially, when people thought about sort of space security or thinking about space in a sort of geopolitical way, there's a lot of analogies about sort of the Navy in the sort of 200 years ago, like deep exploration, blue ocean stuff, right? But actually, the reality over the last kind of 50 to nearly 70, 75 years, whatever, it's kind of much more similar to brown water littoral activity around the coastline of Earth and operating in service to stuff on the Earth. But actually now we're starting to really be able to imagine and perhaps even, start to put into production some of the technology that will give us the opportunity to genuinely go to Mars or genuinely put a cruise base on the moon. And that's going to, give rise to a bunch of new questions. A lot of it is still that kind of geopolitical flex of, are we the first to do it? Look at us. But actually, there are a million reasons why you might want to go and mine different planets for lots of, rare, minerals, for example, or be able to generate fuel on the moon so that you can then jump onto Mars. And kind of, Elon Musk's motto is making humanitarian interplanetary, isn't it? I mean, he hasn't really got a reason why, other than it's there for the same reason as that people wanted to climb Everest back in the day. But I can very much imagine a world whereby we start to discover some useful, sort of resources and think actually this is now going to be a great power politics competition to sort of to own that. Um, and there isn't any sort of legal infrastructure in place at the moment. And I don't think there ever will be, because, the Americans have been very clear about the fact that they don't need any more unnecessary international law. They just kind of want to operate in a sort of, biggest stick type scenario. But the size of the sticks are changing relatively. There's a lot more really, really competent players. It's much more multilateral. And genuinely, the non-state actors are really good now
Yeah.
and are operating in leaps and bounds in some instances ahead of some of the states. So it's going to be an interesting space, and it's really important that we shape our sort of policymakers to understand the importance of trying to
Yeah.
regulate it as much as they can.
Yeah. Thank you. Thank you. Right. Questions. I think we've got a microphone, so if you put your hand up and we'll get a microphone to you. Yes, please.
Thanks very much. I don't know that. Yeah. Okay. Thanks very much for all the panelists. Oh no. Okay. Thank you. Thank you very much to all the panelists for really interesting and sort of informative discussion. Tom, I was going to ask you. I have heard of, obviously the UK has got this space base in Cornwall. They've been doing some stuff down there. But what's the UK's role more specifically with kind of sort of space exploration and where maybe it would work with these non-state operators in the future, perhaps, or whether we would still remain perhaps linked with Europe, or if you could elaborate a bit on that, would be really interesting. Thank you.
I absolutely can. So I mean, the UK would like to be a power player in this, but there are some sort of obvious restrictions. The reason that lots of space bases are on the equator is because physically you get a much better opportunity to kind of launch things into space. If you're at 50 degrees north, the only orbits that you can operate in are between 50 and 90. You can't operate between 0 and 49. So there are some physical limitations. I mean, there are some limitations around how congested the airspace is around Europe. I mean, and it's super complicated because as you have to leave the Earth's atmosphere, you've got to go through a bunch of different countries' flight information. They effectively, space is great because nobody owns space, but people do own the bit up until flight level 100. So you've got to negotiate all of that. So there are some complications. It's not insurmountable. And you saw Virgin Orbit had a really good crack at launching something from the UK. Sadly, it didn't work because putting stuff in space is hard, and it fundamentally bankrupted them. So they've decided to pull out of the investment. But it's not impossible. But the UK definitely see themselves, I mean, as a sort of technological leader, there's a role for the UK to play. And the UK Space Agency, which is part of the government science, technology, and innovation, are very, very keen to kind of put a lot of money into some of the innovation and the sort of technical know-how. And they've spent a lot of money setting up a campus down in Harwell and Oxford. So that's one side of your question. The other side of your question is, where does the UK sit on this in this kind of big geopolitical norm-setting debate? And again, the UK have been very clear about they see space as a domain for peaceful operations. They promote responsible behaviour. They call out irresponsible behaviour. So on that kind of norm-forming international platform, there's a role for the UK government to kind of effectively try and set standards of good behaviour. And I think that's probably a realistic approach with the kind of resources and the constraints that we've got.
Thank you. Thank you. Yes, please. Oh, Cheryl, have you got a question from the online? Wonderful. We don't need to. Oh, yes, we'll give Cheryl the microphone.
Thank you. So a question from Kate online, also directed to Thom. With the suggested cuts to NASA and a current US appetite for cutting regulation and funding for anything to do with green tech and sustainability, who will take the lead on space debris?
Okay, that's a great question. It's a funny one, isn't it? Because, I mean, it's very difficult to know what's happening in America at the moment. It changes so quickly. But what I will say is that in the last in 2019, they stood up a Space Force, which is, pretty paradigm shifting because effectively they reckon, I mean, that was a big investment. So from a security perspective, they're definitely spending more money. I can see the military having a role to play in debris mitigation, which isn't traditionally a military role, but it's just kind of naturally we've got a lot of the sensor technology. And in the UK, we certainly, I mean, 99% of what I did at RF Findingdales was looking to see whether stuff was about to hit other stuff or whether stuff was, stable and or about to tumble out of its orbit and to cause some damage. So there's a role to play. But I also think that, the private sector are going to have a massive, massive role to play in debris mitigation for a couple of reasons. Firstly, because I think that they're going to get a bunch of contracts from the government to do it, but also because I think that the operators themselves are recognizing that if they don't look after their domain, it's going to be effectively fundamentally ruined. And so, interestingly, the corporate entities are lobbying for stricter regulation. So at the moment, there are guidelines around when your space satellite, for example, has finished its usable operational life, it is to be deorbited within 25 years. The national regulators, the industry regulators, like let's make it 5, which is really encouraging, right? Because they're just like this. We can do this. We don't need to artificially limit ourselves. So does that answer the question? I've kind of run away with myself a little bit, yeah, but that covered all the points. Thank you.
And then we've got a couple of questions here. So, yeah, Sir Evan, and we'll come across.
Thank you. So my question is to Amy. So there was recently this huge press coverage on discovery of organic compounds on a planet. So I just wanted to ask, how significant is that? Uh, how strong is evidence of extraterrestrial life?
Yeah, so I think we're in a really exciting time. So this is using the James Webb Space Telescope and demonstrating the amazing capacity that this telescope has to really characterize the atmospheres of these planets and look for trace elements there. Um, I think, as Madison, who's the lead author in that study, would say as well that how to kind of phrase this, the detection of particular biosignatures and the connection with those with life on a planet is still an area where we really need to delve into our understanding deeper and better probe how we can use the information that we have, which is very limited, to make inferences about which are robust about what the planet is truly like underneath. And so, yeah, I think it's a really exciting time. And James Webb, this is the beginning, right? We've now got space to look for other planets, and there'll be more coming.
Thank you very much. Yeah, just across, could you pass the microphone?
So, to your answer, I just want to add a little more to it. Because I worked on many of those research commercial program, and part of the design cycle is now that at the end of the life, all big satellites as well as commercial space station has to deorbit safely and either burn up or it's part of the design cycle now where everything that goes up has to come down in a controlled manner
SpaceX are
before.
really innovative. I mean, they will launch 100 satellites at once, and they're very disposable almost, really. But what they'll do is they'll put them in a sort of a nice safe holding orbit, do an electronic handshake, make sure it works, function test before they put them into an orbit where they could potentially cause some damage. And if they don't work, then they'll deorbit them. But and that's the kind of the point about you're not launching exquisite satellites that are worth $1 billion. You're launching satellites that are really, really affordable, and if they don't work, you just reorbit them, burn them up, and throw up some more, right? But you do that in a way that is kind of affordable and sustainable.
Yeah, thank you. And there was a question.
One quick question for you.
quick-
Uh, does UK government has any plan to to launch a program to still be competitive with the industry and other nations? If you look at it in a recent
So, I mean,
last decade,
is your question that are we launching satellites? And
is the UK government has any plan to do any major program like US or China or
yeah, I mean, so there is sort of some funding for a series of programs around ISR and other capabilities, but actually, I think we're also funding a lot of active debris removal research. So, but I mean, that's probably all I can say on that, really.
Thank you. I think there was a question, yep, just a little further back. Thank you.
Thank you. Can I ask, how likely is, a situation like Kessler described happening? And if it does happen, is that just it, or can that be mitigated?
So just to remind everybody, the Kessler effect is effectively a sort of chain reaction whereby you get a bit of debris pings into another bit of debris, which effectively causes a runaway. I mean, it's pretty likely, right? I mean, we can track debris up to a certain size, but there's a lot of stuff we can't see. And it's very conceivable that it happens. And if it does, I mean, it is a genuine tipping point of the scale of the melting of the Antarctic shelf or the Arctic shelf. In that, once it happens, it's going to be very difficult to come back from that. And we could very conceivably get to a point where we can't use certain orbits. And unsurprisingly, the orbits in which that is most likely to happen are the ones that are the most useful. So yeah, it's pretty conceivable. It's definitely listed as a global risk in a bunch of kind of UN risk mitigation, well, not mitigation, just risk registers lessons.
Very good, very interesting. I think all of you have given this a different perspective, but you've also conveyed the excitement of your fields, the new work that's going on, the cutting edge that's going on. I've got one last question for each of you, if you don't mind, which is, if Elon Musk does get his rocket to Mars in your lifetimes, you're fascinated by space, but would you get in the rocket and go to Mars? Do you want to be out there, Tom?
Spent a lot of my youth in effectively sardine tins. It's pretty boring. It takes 6 months to get to Mars.
So that's a no. Okay, right. Amy?
I think we can do so much amazing research with robots in space. Why do we need to send people?
Good. Mike? No. Okay, and I think I'd be the same, although the views would be amazing. Good, thank you all so much. Thank you also to those of you who've joined us this evening online, but above all, thank you to our wonderful guests. Thank you.